In this video, we're going to study equivalence relations. So an equivalence relation is just a specific kind of relation. So we've talked about relations in detail, and we've also talked about their properties. So this should sort of bring everything together. If we're talking about an equivalence relation, we're simply saying that it is a relation that is reflexive, symmetric, and transitive. And note the notation that we use, we're using that tilde sign, that A is equivalent to B by the relation. So the types of questions that you might get would be they're going to give you some sort of relation and they're going to ask, is it an equivalence relation? So basically that's just saying check the three properties that we know we need to check, and if they all hold true, then it is in fact an equivalence relation. So we'll start with this example where R is the relation on the set of real numbers such that, so again we're starting with a real number and we're saying that A is related to B if and only if A minus B is an integer. So is this an equivalence relation? So we'll start with the easiest property, which is the reflexive property. We're saying A minus A. So if A is related to A, that implies that A minus A is an integer. Well, we all know that A minus A is 0. No matter what A is, A minus itself is 0. And 0 is in fact an integer, so yes, this is reflexive. Is this symmetric? So symmetric says if A is related to B, that implies that B, is related to A. So is this true? So if I took A minus B and got an integer, that's implied. Is it true then, does it imply that B minus A is an integer as well? Well, absolutely that is true. So think of it this way. Let's call A minus B, we'll say that's C. And we know that it's an integer because that's the hypothesis in the implication. So this is true. A minus B is equal to C, which means if I took B minus A, what am I going to get? The opposite sign of C, unless of course C was 0, then I would still get 0. And we know that if C is an integer, then the opposite of C is also an integer. So yes, this is symmetric. So now let's look at the last one. Is it transitive? That's the hardest one. And that one again says if A is related to B and B is related to C, it implies that A is related to C. Oops, I think I used an A here on accident. A is related to B. So the question is that true? Because A is related to C says that A minus C must be an integer. Well, this one says A minus B is an integer, and this one says B minus C is an integer. So this is kind of a tricky way to go about it, but we're going to say A minus C is the same. An equivalent way to write that is A minus B plus B minus C. Now I know this is an integer, and I know that this is an integer, and A minus B plus B minus C gives me A minus C, so obviously I didn't break any rules. So then the question is this an integer? Well, sure. If I take an integer plus an integer, I get another integer. So A minus C is in fact an integer if A is related to B and B is related to C, or in other words, if their differences are integers. So because this relation is reflexive, symmetric, and transitive, then the relation is in fact an equivalence relation. Let's take a look at another example. Now we have, suppose R is the relation on the set of strings of English letters where A is related to B if L of A is equal to L of B, where L of X is the length of string X. They're asking, is this an equivalence relation? So of course we're going to have to check the properties again. We'll start by checking reflexive. And reflexive, remember, means A is related to A. So is it true that the number of letters in the word of A is equal to the number of letters in the word A? Sure. So if the word is cat, then L of cat is 3. then of course 3 equals 3. So now let's look at symmetric. Symmetric says if A is related to B, then B is related to A. And again, so I'm sorry, I should have put yes over here. So is that true? Okay, so again, let's say L of A is equal to 4. There's 4 letters. L of B is equal to 4, which means A is related to B. And then is it also true then that B must be related to A? Well, if 4 is equal to 4, then 4 must be equal to 4. So yes, because L of A is equal to L of B, and L of B is equal to L of A. It's always going to be true. Now let's take a look at transitive. And again, transitive says if A is related to B and B is related to C, it implies then that A is related to C. And again, it's not very difficult for us to figure this out. Let's say L of A is 7 and L of B is 7 and L of C is 7. So does that make sense then that A is related to B? Well, L of A is 7 and that's equal to L of B, so that's true. And L of B is 7 and that's equal to L of C, which is 7. So that's true. So is it true now that A is related to C? Well, L of A is 7 and L of C is 7, and so yes, it is true. So yes, it's reflexive, yes, it's symmetric, and yes, it is transitive. So is this an equivalence relation? Yes, it is. Let's take a look at just one more example. We have is R, which is a relation on the positive integers where A is related to B if and only if A divides B. Is that an equivalence relation? So again, let's just recall what it means to say A divides B. It means A goes into B evenly with no remainder, or B divided by A is an integer. So is this in fact true? So let's start with the reflexive property. The reflexive property says that A must be related to A. So is it true for all positive integers that A divides itself? Well, I don't even need to show an example to know that that is in fact true. 2 divides 2, 7 divides 7, 13 divides 13. We get it. Any positive integer is going to divide itself, and the quotient is going to be 1. So, yes, it's reflexive. Is this symmetric? And remember, symmetric says if A is related to B, it must imply that B is related to A. So that tells me if A divides B, then B must divide A. Well, hopefully you can tell just right off the bat that this is not going to be true, but I can show it fairly quickly with a counterexample. And remember, that's all that's required to show that something's not true is a counterexample. So 2 divides 8 because 2 goes into 8 evenly with no remainder. 8 divided by 2 is 4. But does 8 divide 2? Well, 8 does not go into 2 evenly because I would in fact not get an integer, I would get a decimal. 8 into 2 is 0.25. So of course this does not imply this. So this is not symmetric. So do I have to continue to check the transitivity property? I sure don't. I could stop right there. But just for practice, we'll go ahead and take a look. Remember, transitive says, so of course, sorry, I should be clear. We've already answered this question, and the answer is no, it's not, because it's not symmetric. But again, let's go ahead and take a look at the transitivity property just for practice. This says, if both A is related to B and B is related to C, it implies that A is related to C. And again, this one should be pretty straightforward. This one's saying A divides B, this one's saying B divides C. Does that imply A divides C? And this one is in fact going to be true. So if I take a look at A divides B, let's just look at an example using actual numbers. So 2 divides 8. We already know that's true. 2 goes into 8 4 times. 8 divides 16. So again, these two, it's a given that they're true. So 2 divides 8, 8 divides 16, that's totally true. A divides C is 2 divides 16. And the question is that true? Is it always going to be true and not just true for the example that I made up? And it is always going to be true, because if 2 goes into this number and this number is just a multiple of this number, then it's always going to be true every single time. So yes, this in fact is transitive. Is it an equivalence relation? No, because it is not symmetric, but it is reflexive and transitive. Often when we are talking about equivalence relations, we talk about equivalence classes. And an equivalence class is essentially just a grouping or a set of all elements that are related through a relation. So for instance, if R is the equivalence relation on the set of integers such that A is related to B if and only if A equals B or A equals negative B, and they want us to give the equivalence classes. So let's think about what would happen here. If I'm taking A equal B and A equal negative B, then things that would be related is 1 is related to itself and also related to negative 1. These things would be grouped together. 0 would be obviously just related to itself. There would be no negative value. The value of 2 would be related to the value of negative 2, because that would be A equals B or A equals negative B. And 3 would be related to negative 3, and you get the idea. Now, it's impossible for us to list all of these, so essentially what we do is we use this notation and we say, let's just choose a representative, and obviously it's easier to choose a positive representative. So I'm choosing the representative of 1 for the equivalence class, an equivalence class of 0, and an equivalence class of 2. And again, all I'm doing is saying all of these values within that equivalence class are related. And so to make this easier, I would say that A would include both the positive A value and the opposite A value. So if the original A was negative, then the other one would be a negative negative, which is positive. We get the idea, where of course A is an integer. So this would be an easy way to generalize that. But again, the equivalence class just relates things that basically that are related through the equivalence relation. Let's take a look at a partition example, and partitions are great to help us to understand equivalence relations. But first, before we look at an equivalence relation, let's just look at what a partition is in case you've never encountered one before. A partition of a set S is a collection of disjoint, non-empty subsets that have S as their union. So that's our conditions, disjoint, non-empty subsets that have S as their union. So what does all of that mean? We're saying that if xi is some subset, that it's not empty, non-empty subset. They are disjoint, which means their intersection is the empty set, which essentially means when I partition these values, I can't have an element that's in more than one subset. And then of course, they have S as their union. So the union of all of the subsets is equal to the set, which means I didn't leave anything out, and if I add all of the subsets together, I get the original set. So let's look at how I could possibly partition the digits 1 through 9. I could just randomly partition them. This would be considered a partition. Let's call this A1, A2, A3. Was there any rhyme or reason to how I partition these? No, but does it fit the bill in terms of a partition? Are these disjoint? Yes, because there is not an element in A1 that's in A2 or A3, etc. Are these non-empty? Yes, each element or each subset, A1, A2, A3, all has at least one element. And do they have S as their union? Yes, all of the elements that were contained in my green circle of digits 1 through 9 are all accounted for in one of the subsets. So this is a valid partition. Let's take a look at another that maybe has some reasoning behind it. What if I wanted all of my even values to be together? So I have 2, 4, 6, 8, we'll call that A1, and 1, 3, 5, 7, 9, we'll call that A2. So again, this is a great way to partition them as well. Let's look at one related to discrete math, since that's what we're studying. What if I looked at division mod 3? Well, mod 3, if you'll recall, has everything to do with what is the remainder when I divide by 3. And the only possible remainders when I divide by 3 are 0, 1, and 2. I can't have a remainder of 3 because that would just add one more to the quotient. So 0, 1, and 2 are my possible remainders. So if I grouped 3, 6, and 9 together, any of those divided by 3 has a remainder of 0. So those are the elements that belong to my equivalence class. And again, note the notation. I've got the brackets around the 0, and I chose 0 because that is the remainder. So what about 1, 4, 7? Well, if I divide 1 by 3, I get 0, remainder 1. If I divide 4 by 3, I get 1, remainder 1. And if I divide 7 by 3, I get 2, remainder 1. So this is my equivalence class for a remainder of 1, which is 1, 4, 7. And then again, 2, 5, and 8 all have a remainder of 2. So the equivalence class for 2 is 2, 5, 8. So again, I've chosen some representative for the name or label for my equivalence class, but that is a valid partition because again, no empty subsets, the intersection, there's no overlap. If I add up all of the subsets, they do add up to the set itself. Let's take a look at another example now, and this is similar to the last one. In the last example we did mod 3, however, we only had 9 digits to deal with, and now I'm asking for the partition of integers. So obviously there's going to be more values, but it's the same concept. I can either have a remainder of 0 or of 1 or of 2 or of 3. And so essentially what they're saying is, give me the values that belong to the equivalence class of 0. So we know the values in the equivalence class of 0 would be things that are divisible by 4 evenly. So 0 is equivalent or is divisible by 4 evenly, and 4 and 8, and this would continue on forever in the positive direction, or negative 4 or negative 8 or negative 12, and it would continue forever in the negative direction. So that's how I might write that for the equivalence class of 0. Now let's look at the equivalence class for 1. So I know for sure that 1 has a remainder of 1 because 4 goes into 1 0 times with a remainder of 1. And essentially I'm just going to add 4 and add 4 and add 4. And then I'm going to subtract 4 and subtract 4 and know that it goes forever in each direction. And I'm going to continue that process. So 2, obviously, and then I'm going to add 4 and add 4, or I'm going to subtract 4 and subtract 4. And then for 3, obviously 3 works, and I can add 4 and add 4, or I can subtract 4 and subtract 4. Oof, try that again. 1 minus 4 is negative 5. There we go. Now, the question then is this a partition? So, do I have any empty subsets? No. Do I have any overlap in my equivalence classes? No, I don't. If I added up all of these, is it the set of all integers? And yes, it is. So 0, 1, 2, 3, 4, 5, 6, 7, etc. And then, of course, on the negative side, negative 1, negative 2, negative 3, negative 4, and it continues forever. So yes, this is a partition, and again, these are the equivalence classes based on that partition. We're going to end with 4 examples or non-examples. Essentially, we're going to look at these 4 partitions and say, are they in fact partitions? And so if you'll recall, in order for them to be partitions, we need no empty set, we need no overlap, And again, that's not the official mathematical term. We're saying that the intersection of the sets must be the empty set, but essentially that means no overlap. And is the union the entire set, so all elements included? So these are the things that I'm going to check for each of these possibilities. And I'm just going to write a yes or a no next to them, whether they are partition or not. So for the first one, P1, we're saying we have the subset 1, 2, we have the subset 3, 4, 5, and we have the subset 6, 7. And looking at 1, 2, 3, 4, 5, 6, 7, yes, all elements are included. There is no overlap, which means I didn't use any of those values more than once. However, no empty set is not satisfied because obviously the empty set is included in the partition and it cannot be in order for it to be a partition. So is this a partition? That is a no. And again, if I were doing this for like a homework assignment or a quiz or a test, I would say no, and then I would cite the reason because of no empty set. Let's look at P2. P2 includes the elements 1, 2, 3, 4, 5, 6, 7. That's all of the elements, so all of the elements are included, and I didn't repeat any, so there was no overlap. There's also no empty set, so therefore this is a yes. It meets all three requirements. Let's try for P3. We have 1, 2, 3, 4, 5, 6, 7, but if you'll notice here, 3 was counted twice. So the no overlap is not met. So yes, there's no empty set and all elements are included, but we have an overlap, and so this is a no. And again, I would say for my explanation that 3 was used twice. And then for my last one, I've got 1, 2, 3, 4, 5, 6, but it looks like I'm missing 7. So yes, there's no empty set and there's no overlap. However, not all elements are included, so this is a no. Up next is a great introduction to graphs. And we are not going to study graphs in detail in this course, but we are going to be introduced to graphs and some of the terminology used in graph theory.